Okay, let's key in your attendance there. Okay, class, so let's start. Okay, so today we cover the X-ray. Okay, we finish off the X-ray. After X-ray, we continue with CT scan. Okay, CT scan is very short. Okay, after CT scan, we see some videos. Okay, that's our plan today. Okay. Okay, let's go back to the slide. Okay, recall back what we learned about X-ray. So how X-ray produced? 2 marks. So X-ray produced how? When a high-speed electron. When a high-speed electron was accelerated and bombarded to a metal surface, the kinetic energy of the electron is converted to X-ray. Okay, so keyword is high-speed electron bombarded to a metal surface, kinetic change to X-ray. X-ray and heat, of course. Yes, stated 10%, but in reality, it looks like a 1% change to X-ray. Okay. Then we talk about this graph. So how the production of X-rays, Brunstolong X-rays. Okay. So 7 marks they will ask you to explain. Okay. So why the X-ray is in a range? So how do you explain why the X-ray comes out from the tube is in a range? The first point you must tell is any charged particle accelerates, emits EM radiation. 1 mark. Okay, because the electron makes a range of a series of acceleration, therefore a range of wavelength is produced. Okay, 3 marks explaining that. Then why there is a cutoff? Why the certain minimum wavelength was observed? So how do you explain this? This is due to what? Due to when an electron makes an head-on collision, all the kinetic energy converted to one single photon, which results to this cutoff wavelength. Okay, 2 marks. Then 2 marks they ask why there is a spike, why there is certain maximum intensity is observed. Okay, this is due to what? 2 marks. How do you explain this? When an incoming electron collide with the initial electron, the electron will be excited. When de-excitation happens, it produces emission spectrum. Okay, emission spectrum. We discussed about emission spectrum under quantum last time. When the electron goes down, it from high energy level to low energy level, it releases emission spectrum. Okay, yeah. So remember about the graph. Then of course, when the voltage rises, this is how the area increases. Minimum wavelength increases, but the spike happens the same location. It depends to the nature of the metal used. Okay, the anode used. Okay. Okay, that's what we discovered, the first one. Okay, then we talk about X-ray intensity. How you rise the intensity, increase the tube current. Okay, the current in the filament, you rise it, more electron will be free. So more electron going to collide with the anode. So more X-ray photons will be produced. So more intensely. Okay. Then we get into the what is meant by hardness. Okay, more penetrative power. Hardness means how big is the penetration power. Okay, short wavelength X-ray will have a greater hardness. Okay, how do you increase hardness? Rise the voltage. Okay, the voltage, you rise the voltage, the kinetic energy of the electron will be raised. So when it collide, it capable to produce a shorter wavelength X-ray. Okay, which is more hardness, greater hardness. Okay. So next time they ask what is meant by hardness, you say it's a penetration power of the X-ray. Okay, then we talk about soft X-ray need to be blocked, so we use an aluminium filter. Okay, yeah. So the formula to calculate the minimum wavelength, EV equals HCO lambda. Okay, then we go for X-ray imaging. The image must be, we try to make it very clear imaging. How do you make it clear? We focus to two important features of the imaging: sharpness and contrast. So you should know how X-ray image sharpness is increased, how the contrast is increased. I think that day we only discussed about the sharpness. The definition, remember. So what is sharpness? Yeah, with the ease with which the edges of the structure can be determined. How clear you can see the two medium, the border of the two medium. Okay, it's sharpness. Okay. So contrast is the differences in the degree of blackening of two mediums. Two mediums. Okay, so how do you improve sharpness? Two ways. Smaller anode to be used so that partial shadow is smaller. Okay, then filter, make the anode smaller. Then we use a lead grid. Lead grid blocks the diffracted X-rays so that the image is more sharper. So we use lead grid, we use a small anode. Okay. Now we talk about contrast. Okay. So of course, although the image is sharp, but the two medium is same darkness, you can't differentiate which is which. Okay, we need to have some sort of a contrast. Okay, so how to improve contrast? Okay, but this is very rare. The first method they use is they ask you to inject your body with a contrast medium. So stomach may examine, if especially they want to see the stomach. Okay, the blood flows by giving a patient a drink of containing barium sulfate. It can outline the blood vessels. So when X-ray will be absorbed, and it can really give a good contrast to the blood vessels. Okay. So anyone want to check the blood vessels in the stomach? So contrast medium is used to improve contrast. Okay. Actually, there are three factors affects contrast. Like you want to rise the contrast. Okay, the first one is the exposure time. Okay. You expose the X-ray for a longer period of time. Let's say, for example, like this. You expose the X-ray for a longer period of time to the patient. The region where the what do you call the X-ray strikes the most, the soft tissue, that region become even darker. It get darker and darker because photographic chemical reaction happens, so it become dark. So more longer time the X-ray hit the plate, more darker that region become. The soft tissue region become more darker, so it can give a good contrast compared to the bone. Okay, so of course contrast can be improved by using a exposure time. But it's not a good idea. How can you're going to stand there for 5 to 10 minutes, you're exposed to X-ray, you're going to kill a lot of your cells, so harm your body. So not advisable exposure time. Okay. Contrast medium, I think maybe a good alternative compared to exposure time. Yeah. And of course, the origin, the X-ray penetration also affects the contrast lah. Like as I said, if the soft tissue bone, of course, bone absorb the most, so it can give a good contrast. So scattering of X-ray beam within the patient body. So another way of improve the contrast is you can see the doctor when they got the photographic plate, normally put on the light, and on the light it's a fluorescent light. Fluorescent material is used to improve the contrast. So I think these are the two advisable technique. Either use contrast medium or use a fluorescent material later to improve contrast. So what is contrast? Remember, difference in the degree of blackening of the image between one organ to another or one tissue to another tissue. Yeah, so that's how to improve contrast. Okay. Okay, so nowadays, as I told you, if current lifestyle, I think people who are getting close to 50s already get some sort of a cardiac problem. Heart block now become very common. So when the people go to hospitals, best method to check whether 100% to make sure that you have block or don't have block, angiogram. Okay, so how they do the angiogram is actually they use actually an X-ray. They use an X-ray to show the real-time imaging of the heart. Okay, the heart. So, but they don't want to see the heart. They want to see the blood vessel of the heart. Okay, so what they do during the angiogram, they will inject a dye. They inject a dye. They let the dye to flow into the blood vessel of the heart, the coronary, what do you call it? The coronary blood vessel. Okay, then when they release the dye, when the dye flows in the blood vessel, they monitor how the dye is flowing. If the dye is suddenly, the flow is not smooth, suddenly blocked, they know where's the block is there, if there is a block or not. Okay, so the dye is used to improve the contrast of the imaging. If you don't have a contrast medium, difficult for us to see the blood vessel of the heart. Okay. Yeah. So, two ways to improve sharpness: smaller anode, lead grid. Two ways improve contrast: contrast medium, exposure time, fluorescent material. Three ways lah, but exposure time is not advisable. Yeah. So this is about some facts about how to produce a quality image of X-ray. Okay. Any questions so far? It's a fact to remember. No calculation. Okay, so we are almost done. X-ray. Okay. The last part we're going to talk about X-ray is something called attenuation of X-ray. Okay. Actually, the term attenuation is used in telecommunication. What is meant by attenuation is reduction of power. Reduction of power. In telecommunication, we say reduction in the signal power, attenuation. Okay. In X-ray also they use that term. In X-ray, the attenuation means refers to reduction of the intensity of X-ray. Okay. Reduction of the intensity of X-ray. Okay, right, when the X-ray get into the body, okay, when it travel for a certain thickness of soft tissue, let's say, the X-ray beam received and emitted will be different. Some intensity will be absorbed, like what happened for ultrasound. Okay, ultrasound when get into the bone, the ultrasound will be absorbed, right? Not only in the bone, you go to the soft tissue also, some ultrasound will be absorbed. Okay, we discussed about that, the absorption coefficient and everything. Bone has the greatest absorption coefficient. Okay, same thing happens for X-ray. Okay, so we call it attenuation of X-ray. So now similar formula was found for X-ray too. So like ultrasound, the I is the intensity after passes a certain thickness of tissue. The I naught is the original intensity, and the mu is called absorption coefficient, which is depend to the tissue, and X is the thickness of the tissue. This formula is exactly same as ultrasound. Ultrasound also use the same formula, right? Instead of mu, you put K, right? You got X, thickness. K in ultrasound also absorption coefficient, I naught. Okay, so similar, like ultrasound. And again, be careful if any calculation question asked about what is the intensity after passes the thickness of X. Make sure the mu and X has the same unit. Same unit means if the X is centimeter, mu must be in per centimeter. Okay. Yeah. But they will trick you. The mu, they have variety of unit for mu, because length, right? Per millimeter, per centimeter, per meter. So make sure the units is the same. Okay. Okay, so yeah, so because the absorption happens exponentially, this the graph tells you, the original intensity, let's say 100, you use a certain thickness, let's say this thickness called half thickness, like half life, we got half value thickness. So what is half life? The average time taken for the radioactivity, the activity to drop to half of its initial value. The same definition for half value thickness. So what is the half value thickness in terms of X-ray? So the thickness of the medium required to reduce the transmitted intensity to 1/2 of its initial value. This is called half thickness, half value thickness. So half value thickness is the thickness of the tissue required for the X-ray intensity drop to half of its initial value. It's called half thickness. Very rare they ask question about half thickness, but anyway, you have to know what is meant by half thickness. So half thickness, from this formula, actually this formula, you can find the half thickness. Okay, go to the whiteboard. Okay, yeah, so I equals to I naught E negative mu X. Okay, right? When thickness is the half thickness, then I become I naught over 2, right? Yeah, so I naught over 2. So of course, I naught over 2, I naught E negative mu X. Okay, bring ln both sides. Okay, so we got ln both sides, so it become ln half, right? So it's ln 2, negative ln 2. So here bring ln, I think you get I naught cancel. I naught cancel. So negative ln 2. Here you got mu X. Okay, I jumped few steps already from here to here. So yeah, from here, so no negative anymore. No negative anymore. So negative cancels. So ln 2 will become mu X. Okay. So same like your half-life derivation. Okay. So that's what's shown here. Okay. Just now the half-life, half thickness times the mu is actually ln 2. Okay, it's ln 2. Okay. So remember for half thickness. Half thickness times mu is ln 2. Actually, it originated from this formula. X is X half, I is I naught. Get this? Yeah. So in practice, the half thickness does not have a precise value of its constant only when the beam has proton of one energy only. Yeah, correct. Okay. It depends on the energy of the photon to produce it. Okay. So that's all. So one example. One example about the thickness, about absorption. Look at the question, look at the solution. This is exactly same as like your half-life, as I told you. Look at the first one. Read the question and look at the solution. The linear absorption coefficient of a copper is 0.693 milli per millimeter. Calculate the thickness of the copper required to reduce the incident intensity by 50%. Here the incident intensity is the X-ray intensity actually. X-ray is sent to the copper. What is the thickness of copper required so that the X-ray intensity drop to 50%? Same. So I equals to I naught negative mu x. Yeah, of course. The I become I naught over 2, right? I over I naught is 0.5. Yeah. Okay. So make sure the 0.93 was in terms of per millimeter. So when you find the x also will be in terms of millimeter. Okay. So for copper is found to be half thickness is 1 millimeter. Okay. So in the case of B, what they want? The fraction of the incident intensity of the parallel beam that is transmitted through a copper plate of a thickness of 1.2. The fraction of the incident intensity. Fraction of the incident intensity. That means they are looking for what? I over I naught, right? They are looking for what is I over I naught value. Yeah. Fraction of the incident intensity. I over I naught value, right? Yeah, so I over I naught is E negative the K and the mu and X. So X is 1.2 centimeter. So this is the trap, as I told you. The unit of mu and X must be the same. So here purposely given 1.2 centimeter. So it changed to millimeter because the K was in millimeter per millimeter. So rewrite 12 millimeter. Then you get the answer. Fraction. I don't know how many times you have come across with this type of equation. I equals to I naught E negative mu X. Many cases, the first time you come across this exponential equation is in the capacitor. Okay, the discharging current I equals to I naught E what do you call negative T over tau, right? Negative T over RC. Yeah, this is the equation you got it from the capacitor exponential. Then second formula you get this exponential from the half-life. The n equals to n naught E negative T what do you call negative lambda T. Negative lambda T. Then now before X-ray you get no intensity equals to I equals to negative kx for ultrasound, and now X-ray. Okay, so all decreases exponentially. But half values only was focused for half-life and the X-ray, half thickness. Okay, any questions? So hope you got the understand the solution. Okay. Yeah. So that's all about X-ray. So X-ray, I go like summary. What you need to know is what is most of the time has been asked is this graph. Okay, 7 marks explain. Okay, then they ask about what is meant by hardness. It's a calculation, not a calculation question, facts. And how do you increase the hardness? How do you do what do you do to in the tube to increase the hardness, rise the voltage? And how do you increase the intensity, rise the tube current? But this one is not really they asked many times, not even once, I think. They asked about hardness, yeah. Okay, but the earlier graph is very common, they ask. Then what else they ask is, of course, this calculation. There are only two calculations here. Two calculations. One to find the minimum wavelength. This is quite common. What is the minimum wavelength released by the from the X-ray tube? Okay, so EV equals to HC lambda. Very common. This calculation. This is specs again. They'll ask about what is meant by sharpness, what is meant by contrast, how do you improve it. Okay, these facts to remember. Then finally, attenuation, absorption. This also quite common calculation. But this calculation not that difficult. Just you know the thickness, you find the final intensity comes out. Sometimes they can trick you also. They'll ask, what is the intensity absorbed inside the medium? So of course, is what is the intensity absorbed in the medium? Is actually I naught minus the I, right? I naught minus the I is your intensity absorbed in the medium, right? They sometimes they do ask that to trick you. Okay. So remember the I here is the intensity that is emitted. Okay. Still emitted after passes the tissue. Okay. Okay. Yeah. So that's all. Any questions, guys, about X-ray? We'll be continue with CT scan. Okay. So I show you one video first for X-ray, like a summary. Then we go to CT scan. Okay, the first is X-ray. Okay, just 3 minutes, I think. 2 minutes, short one. Okay, try to listen.
Wondered where X-rays come from. Maybe they're created than the average X-ray student have wondered where X-rays come from. Maybe they're created by magical wizards. Maybe they're harvested from unicorns. Maybe X-rays aren't real at all. Obviously, you understand that X-rays are real, and this lesson is about the main principles of X-ray production. X-rays are real, and they have to be created in a very specific way. There's really 3 requirements of X-ray production: a source of electrons, a means of rapidly accelerating or energizing those electrons, and finally a means of rapidly decelerating or de-energizing those electrons. If any of these requirements are missing, X-rays will not be produced. In radiography, all 3 steps of X-ray production take place inside of the X-ray tube. Electrons are produced in the X-ray tube at the cathode filament. The specific process is called thermionic emission, which is the release of electrons, ions, in response to heat. And so it makes sense that it's called thermionic emission. A current running through the filament causes it to become extremely hot, so hot that electrons are actually dissociated from the metal and form an electron cloud around the filament. This is kind of like the filament in an incandescent light bulb. A current running through the light filament creates heat, which creates the light. In an X-ray tube, the filament gets so hot, it actually creates free electrons. A cloud of electrons doesn't do us much good, so what happens next? That's where the unicorns come in. Not really, but the second step of X-ray production is accelerating these electrons, which gives them extremely high kinetic energy. This is accomplished by an electric voltage that we call kilovoltage potential, or better known as kVp. The kVp creates a strong negative charge in the filament that forces the electrons across the X-ray tube. This makes sense since opposites attract. The electrons are repelled by the negatively charged cathode and attracted to the positively charged anode. The last step in X-ray production is decelerating the electrons. These highly energetic electrons slam into the anode of the X-ray tube, and in the process of decelerating, they actually release their energy as heat and, more importantly, as X-rays. The number of X-rays and the energy of X-rays are actually controlled by you, the technologist, using the MA and the kVp. Increasing the MA, or the tube current, increases the number of electrons produced in the X-ray tube. Increasing the number of electrons increases the number of X-ray photons. And this is the idea of intensity. The effect of kVp is slightly different. Increasing kVp, which is the tube potential, increases the energy of the electrons in the X-ray tube, and increasing the electron energy actually results in increased X-ray energy. So that makes sense. In summary, X-rays are not produced by magic or by unicorns. X-ray production requires 3 basic things: a source of electrons through thermionic emission, a means of accelerating those electrons, that's the kVp, and a means of decelerating the electrons, which is what happens when the electrons slam into the anode. MA is used to control the number of X-rays, and kVp is used to control the energy of those X-rays.
Okay, class, this is just a small description summary. Okay. Okay. So we done about X-ray. So we go to more advanced type of scanning after this, CT scan. Okay. Okay. So far we learned about ultrasound. We learned about X-ray. Okay. Now we go to the third one. Okay. This topic we have 4 type of scanning we're going to discuss. So we're done with the third. This is the third one. We done 2. This is the third one. We have another one to go called PET scan. Okay, CT scan is actually previous syllabus CT scan is a little wider, but now they make it very so small. So they never really we teach them quite advanced last time. Okay, so what is CT scan? Okay, so it's called computed tomography scan. Okay, it's called CT scan. It actually uses X-ray. This is also X-ray. Okay, so you go for X-ray or you go for CT scan, you get ample of radiation. Okay, going for X-ray just one shot. Okay, but going for CT scan, the X-ray going to pass through your body for many times. Okay, so what I would say, CT scan is more dangerous than the more dangerous than the X-ray actually, because high dose of X-rays will be passed through your body. Okay, so CT scan it looks like a donut again as usual. It's like a tunnel. You have to go into the tunnel, so there will be a on top you will have a X-ray tube releasing the X-ray. At the bottom you will have a detector, like showing in the second image here. On top is X-ray tube, down is the detector. But how this different from the earlier X-ray is, this X-ray tube will rotate. It will rotate. Okay, it will rotate. That means it's not taking the image of the upper image. When it rotate, it take the side images. Okay, so it's all the side images. So that means it take the images at every angle. Okay, every angle. Okay, then that all the images will be combined to give a 3D view. Okay, yeah, CT scan is technically more better than X-ray. X-ray just give you a 2D shadow image. It's a 2D, but CT can give you a 3D view. Okay, 3D view and a slices view. Okay, yeah. So let's go through these points. CT scanning is, of course, is a computed tomography. Actually involves X-ray tube that turns 360 degrees around the patient. Okay. Yeah. In this way, information is acquired from different angle in a plane. This information will be reconstructed by computer techniques into a slice of cross-sectional area of the body. That means what the image here does. Okay, what the image here does, I show you. Okay, with this. Okay, let's say this is the head of a person. Okay, so so the CT scan will shine at a different angle, and it will be shine in a different slices also. Okay, so let's say they have a small tumor here in the head. Okay, so they will see the first slice of image, second slice of image, third slice of image, fourth slice of image. So the doctor will get the slices of image, okay, on the screen. Okay, maybe the first slice image is here, looks normal because very far away from the tumor. Maybe the fourth image, okay, started to cut the tumor, so they start to see an abnormality at the fourth image, and they monitor 5, 6, 7, so they can see how big is the tumor. So the CT scan capable to give a slice images, okay, and it can give a 3D view also. Okay, they can rotate this picture so that show a 3D view to tell that what is the size of the tumor. Is it a perfectly sphere or is a little elliptical? something like that, some view. Okay. Okay, yeah. So the information is reconstructed by a computer technique into a slice of cross-sectional. This is why I told you, slice of cross-sectional image of the body. Slice by slice can be seen. Like you see here, the radiologist seeing the slice by slice. Okay. When he move the what do you call the cursor, the slices will be added. The slice 1, slice 2 will be added. Okay. So doctor just go through this slice, he can see the abnormality if there is any. Okay. Okay, so this technique is just in midst of 20th century CT scan. X-ray was detected. X-ray was discovered in the late of 19th century, 1895. But the CT scan, I think, the midst of 20th century has been developed because we need a strong computer. What do you call hardware and software. Yeah. So the image of successive slices can be combined to give a 3D dimensional. These slices can be combined to form a 3D view. Okay. So this is one slice images. Okay. Okay. CT scan can say it's a high level of scanning. The low level, as I told you, the first day, if you go to the hospital, you stomach pain or something or anything, first they go for the primary scanning is of course X-ray and ultrasound. Okay, and the X-ray and ultrasound found something abnormality, and the doctor want to know more detail. Then he will ask you to go for a high level of scanning, of course, CT scan or MRI. So CT scan has some advantage. Okay, what is the advantage? This advantage is compared to MRI actually. Compared to MRI, CT scan is fast. Okay, it's very fast. You only going to stay in that tunnel maybe less than around 10 minutes lah. This just scanning only 10 minutes. But to prepare you before CT scan might take about half an hour lah. Inject the dye and everything. Okay, but the scanning alone can be within 10 to 15 minutes done with the scanning. So it's quite fast. MRI can go up to 45 minutes. Okay, so MRI is not fast. CT scan is fast. CT scan is patient friendly. What is meant by patient friendly? CT scan, when you get into the tunnel, you no need to stay still. You can move a little, doesn't matter. Of course, you're not going to move a lot. Okay, but MRI you have to stay still. You move a little, then the image will be distorted. So you're going to pay again to get a new shot. Okay. So yeah, so CT scan is patient friendly. You don't need to move. You don't need to like stay still. Okay. Yeah. So it has a unique ability to image the soft tissue, bone, and blood vessels. It's a all-rounder, quite a versatile type of scanning. Okay. Especially for bone, for brain, blood vessels, CT scan will be useful. CT scan and also MRI is good enough. Both are good. Okay, yeah. So the physician can selectively window the digital CT scan images on a computer monitor to look the soft tissues and the bone and then blood vessel as needed. Yeah. Okay. So it also preferred to method for diagnose lung, liver, and pancreas cancer. So yeah, so as I told you, it's like a tunnel. Okay, so you go in. On top you have an X-ray tube. At the bottom you have the X-ray detector, which is going to be rotated. Okay, will be rotated. Yeah, while it's rotating, when you go one round, you start to go inside. You go to inside. So you take one cross section, then you go to the next cross section. Okay. So what I'm trying to say is, just go a few slides. This is how it scanning. Okay. So conventional CT scanning. The CT scan takes picture of a slice of the body, like slices of a bread. Okay, go one round. Okay, these slices are a few millimeters apart. So how it does, while you make one round, your body will move away. So you go to the next part of the body. You go just rotating. Okay, the X-ray just will rotate. You're just moving along the track. So yeah, the helical CT scan takes continuous picture of the body in a rapid spiral motion, so that there is no gaps in the pictures of the collector. Okay. Yeah. So this is the. But when you go to hospital, not only CT scan looks like this shape, like a tunnel. MRI also like a tunnel. Both cannot differentiate both. It looks the same, but we only can differentiate at the door. At the door, they put a radioactive sign, and then it's a CT scan. For MRI, they put a magnet sign. Okay. Yeah. Okay, guys. So I don't want to drag this further because you're not going to learn in depth about this CT scan. Okay. I straight go to the point. Okay. This is lots of information here for you to read if you want to read it. Okay, but not that important. It's all extra information. Okay. So what you need to know is, I straight go to the point. This is all extra actually. Okay, so what you need to know is this few last slides. Okay, you have to know the differences between X-ray and CT scan. Okay, so there are 5 differences. Okay, first difference is, of course, X-ray is what is an image taken using an X-ray directed in one direction. Okay, CT scan is many images of slice taken at different angles. X-ray is a 2-dimensional image. CT is a 3-dimensional image. Okay. X-ray image is formed on a photographic film plate. Okay. But now currently we don't have photographic film anymore. Now the X-ray is shined to digital sensors, right? So now you go to the hospital, you take X-ray. They're not going to give the photographic film anymore. Okay. The image is digitalized, and the file is sent to your doctor straight away. So you just go to the doctor's office. The doctor will click from there. You observe from the computer. I think 1980s, 90s, early 90s photographic film. So X-ray is sort of photographic film. CT scan, the image all is stored in the computer. It's a data. It's a digital data. Okay. X-ray image is fixed. CT scan, the image can view slice by slice and can be rotated for 3D view. Okay. So X-ray, of course, a low resolution. CT scan can go for high resolution. Okay, so this is the facts you have to remember, the difference between X-ray and CT scan. Okay. Okay. So another one thing you need to remember about CT scan is, okay, as ultrasound, last time we got 6 points to remember, right? The CT scan also, the part B. These are the important things you have to remember about CT scan and X-ray. Yeah, so distinguish between image produced by CT scanning and X-ray imaging. Just now we discussed this A in this table, right? The differences. Okay, this is actually the Cambridge mark scheme. The CT scan is a slices of image can be combined to form a 3D image. X-ray is actually a shadow image. It's a 2D image on a photographic film. Okay. Okay. B. What is the principle of CT scanning? Okay, this is what the 6 point you have to remember. As ultrasound, you have to memorize these two. Okay, if question comes out, explain the principle of CT scanning. It's a gifted mark actually, 5 to 6 marks. Okay, so X-ray image of slice taken for many different angles. These images are combined, repeated for many different slices. To build up a 3D image, the 3D image can be rotated. A computer is required to store the processed huge quantity of data. Okay, that's why this technique is only available in the mid 20th century. Okay, 1950s, 1960s, we got a CT scan. CT scan. Not to say very old technology, just about 70 years old. But MRI is even newer. MRI. Okay. But unfortunately, your MRI has been removed from your syllabus. Okay, guys. So CT scan. Just remember these 6 points. Okay. Remember the differences. CT scan with X-ray. Actually, both are using X-rays. A CT scan is more high technology. Okay, then more questions because it's linked to X-rays. Okay, so this is a question about X-ray. This is about like the points explaining the graphs. So a typical spectrum of X-ray is produced. So why there is a continuous spectrum of wavelength is produced? 3 marks. Okay, so these are the points I asked you to highlight it. The first point you have to tell is always whenever a charged particle accelerates, it produces EM radiation. You see, it's an M1 mark, it's a method mark. If you tell the other 3 points, but you never mention the charged particle accelerates, emits EM radiation, you don't get any marks at all 0. Okay, so the first point is a very important point for you to tell when you explain about the range of wavelength. It's M1 mark. So then after that, right, wavelength depends on the magnitude of the acceleration. Electron have a distribution of acceleration. Therefore, a range of wavelength is produced, continuous spectrum. Okay, then 2, why does a sharp cutoff? Of course, the emission spectrum, right? When electron loses its energy, why sharp cutoff? That means why there is a minimum wavelength. This happens when the electron make one collision. All the electron energy converted to a single photon. Results to a sharp cutoff. Okay, and the spike, again, many times I repeated that. Why spike happens? When the incoming electron collide with the initial electron, the electron excited. When de-excitation happens, it produces emission spectrum, which is responsible for this spike. Okay. Yeah, so this is again about X-rays. This is the mu changes with this is the absorption. Variation with the photon energy of the linear absorption coefficient X-rays soft tissue is illustrated. So the absorption coefficient is dependent to the what do you call the energy, the voltage applied to produce the X-ray. Okay. So explain what is meant by linear absorption. Actually, explaining the equation to explain the linear absorption. This is very weird. So parallel beam is matter, I equals to I naught. So you explain what is meant by I naught, mu, and X. Mu is the linear absorption. Okay. For one particular application of X-ray imaging, electron and the X-ray tube are accelerated through a potential difference of 50 kilovolt. To explain why it is advantage, filter out low energy photon. I already told you, right? Low energy photon doesn't contribute to the imaging. Okay, it's unnecessary radiation. Okay, that's why I need to filter out. Low energy photon absorbs more readily. Photons are less penetrating. Low energy photon do not contribute for the imaging. It just damages the tissue. So it need to be blocked. Okay. Okay. So yeah. So again, the same idea. What is meant by imaging for the CT scan? So remember the 6 points for CT scan. Okay. So that's all about CT scan. So the last part you have to remember, just summary, the 6 points, how the CT scan producing imaging, what is the difference between X-ray and CT scan. Okay. Okay. Let's go some videos again to strengthen the idea of CT scan. I got 2 videos here. Okay. Let's go to first one. Okay. Try to watch.
A CT scan is an X-ray procedure that creates cross-sectional images with the help of computer processing. CT images are more detailed than conventional X-ray images and can reveal bones as well as soft tissue and organs. A conventional X-ray uses a fixed tube that sends X-rays in only one direction. while a CT scanner uses a motorized X-ray source that shoots narrow beams of X-rays as it rotates around the patient. There are special digital X-ray detectors located directly opposite the X-ray source. As the X-ray passes through the patient, they are picked up by the detectors and transmitted to a computer. Image slices can either be displayed individually in two-dimensional form or stacked together to generate a three-dimensional image that can reveal abnormal structures or help the physician plan and monitor treatments.
It's like the summary. Yeah, another one. We go to another one. Okay.
To make a diagnosis, decide about what treatment you need, or find out if your treatment is working.
Hiya, nice to meet you.
This type of scan takes a series of X-rays and uses a computer to put them together.
I'll come back to see you.
Before your scan, you may need to drink either half a litre of water or a type of dye called a contrast medium. This helps to make the scan clearer.
So you're going to feel a bit of sharp scratch.
Before most scans, you have a small tube put into your vein which connects to a drip containing the dye. Again, this helps to show up the inside of your body more clearly on the scan.
Need you lying up on the bed on your back, head on the pillow, feet that end, please.
During the scan, the bed moves in and out of the scanner.
Will move in and out.
You may find it a bit noisy.
So shout if you have any problems. I'm just going to connect you up.
As the drip goes in, you'll probably get a metallic taste in your mouth, feel warm, and you might think you are passing water. You're not.
Just close your eyes, please.
These feelings pass quickly.
Okay, you can open your eyes now. I'm going to be doing the scan shortly, all right?
The radiographer controls the scan from a separate room.
Table moving.
The CT machine takes pictures of your body from different angles and builds up a series of cross-sections. This creates a very detailed picture of the part of your body being scanned. Most scans take just a few minutes.
Okay, that's all finished.
The whole thing takes about 90 minutes, and you usually get the results within a couple of weeks.
Okay, class. So yeah, so there are lots of videos you can watch, right? YouTube. Okay. So yeah, so that's all about CT scan. Okay, any questions? So the medical physics, the 14th topic, I would say that the calculation is only about 20 or 25%. About 70 to 80% is like facts for you to remember. Okay. The next one also the PET scan. The last one we discussed on Monday. It's about that's quite a little interesting than the other three because that involves radioactive substance. You need to inject radioactive substance into your body to find the cancer cells. Okay. So we will be discussing on Monday. Okay. So that also basically facts. Okay. Completely facts for you to remember. Okay. Okay, so any questions? Okay, no questions. Okay, so I see you back on Monday. So thanks. If you have any question, you can stay back as usual.